When you have followed my YouTube channel, you will perhaps know that I am in a certain way always busy searching under old radio magazines, especially from the 1960s, 1970s, 1980s. And this is a 1980s article found via radiohistory.com on the British magazine of, here, the British magazine Radio Constructor. There are two articles about this electronic circuit. Say, a beeper, a ceramic plate that starts to oscillate and gives out a very fierce sound. Not always, by the way, but anyway, here are the two articles. 1981 July, page 658, 1981 February, page 342. And here you see some of these plates. They are very, very, very common. You find them especially in clocks, etc., where they start to beep when you have to wake up, get out of your bed at a certain time. Anyway, so these are, say, the typical beepers, and you see them also in this article. So here, exactly the same. Has everything to do with the so-called piezo-electric effect. That means that there is a crystal plate, and we add two points, say, to two surfaces of that crystal plate a voltage, and it means that the crystal plate bends. Also here. But when we add AC or take such a plate into an oscillator circuit, it will make an audible frequency. So let's see further what this beautiful article can bring us. There are a few things to tell. I tested this circuit. It didn't work. Say, it's a kind of op-amp circuit where the piezo-electrical crystal is connected between the output here and the input. It didn't work. This is also very interesting. Here we have the situation where we have an ultra high output, but the issue is in a certain way that we need here a coil, and that coil must be tuned to exactly the same frequency as the piezo plate here. And for many hobbyists, I know that is a problem to make coils. Anyway, so my circuit that I will publish in this video is not made with a coil. This is an oscillator, of course. Well, for experiments it is very, very interesting. I'm absolutely sure. And also my circuit does not give out an enormous piezo-electric sound in the audio range, but anyway, I only want to give a demonstration about the principles. Here is also say a kind of usable circuit. The output to the piezo-electric element is given by, say, a MOSFET or a chip. But they tell in that article that the energy sent out by the chip is in fact not high enough to make to give out a very fierce sound, but there's also a part in this article where they tell that there is a kind of voltage doubler on AC, in AC terms anyway, that makes that the crystal can be driven out properly. This is a kind of end stage to drive such a piezo-electric plate. Here is a coil. I don't publish it because coils are, say, in a certain way, sometimes, not always, cumbersome to make them anyway. Well, here are again the piezo-electric beeper plates, ceramic plates, and I want to go now to my workbench, and here is my demo circuit. Well, first the schematic again for a certain time. I have already explained that here are the sources. Here is that schematic. There is a PNP transistor here, an NPN transistor here. They oscillate because there is a coupling capacitor here, 0.1 microfarad. It sets the frequency. That's very important to tell, because such a ceramic beeper works at its best when the oscillator frequency is matched to the ceramic beeper, to the plates, and they are here. This is the beeper. Anyway, so you can change the frequency somewhat by using this 100K potentiometer. That's also one of the reasons that I always use here in these cases a bias potentiometer. This is in fact a bias potentiometer via which you can set the voltage where you want to use it between 3 and 9 volts, and the frequency. Frequency is also set by the value of the cap. So I tested it with 0.1 microfarad, 100 nanofarad and 50 nanofarad. 50 nanofarad, the frequency goes up. So after all these talks, let's listen. Here you can hear the resonator, and it's important to tell that sometimes you don't hear anything. So when I pick it out of the here, you don't hear anything, but when it is connected to a certain plate, a certain hole, that acts as a kind of amplifier for the sound. So that's a good idea. Let's try to go to the higher frequencies and demonstrate the function of the bias potmeter here. So it suddenly stops. Well, that's not okay, of course, but let's turn that potmeter again. So like I told, the potmeter has an effect on the frequency. Completely logical when we look to the radio theory. Anyway, well, now we are on 9 volts approximately. Let's go to higher voltages, see what happens. Of course, the frequency goes up. And now we are on 24 volts. And when you look to the old schematics, you will sometimes see that they use a quite high supply voltage to make it working. Anyway, turn the voltage back. here there is a kind of moment where the voltage is so good that we have the maximum audio beeper energy in the order of 1000 hertz, 2000 hertz, 3000 hertz out. And that frequency band, the human ear is especially sensitive for that frequency band. So anyway, that is more or less everything to tell. Back to the schematic again, and thanks for watching. There's not so much more to tell. You can change this capacitor here to 50 nanofarad. Frequency goes up. That is will of course also depend on the beeper that you use. They are in general all made for audio bands, so it means that in that respect they differ not much. We also know ceramic transducers that work in a very high audio range, say 30 kilohertz, 50 kilohertz, etc. But that's not the case here, and of course they are more or less often used in professional circuits, etc. Well, thanks for watching. Again, let's listen to that beautiful sound when it works again. I hope that it works again. Well, anyway, that's electronics. So, yeah, well, there it is again. The voltage was not added. So, it works nice. And again, thanks for watching.